Well, I'm really glad to be here, and I'm hoping to have the opportunity to talk a lot about some of the projects we're doing in terms of self-configurable systems. What I'd like to talk about today is agile systems and agile hardware systems for embedded computing. I think if we look at a timeline, if this is now, the things that I'd like to talk about today are a little bit into the future. Relative to the topics that you're discussing in this class are probably way out here. The main topic, the sum matrix work, is really stretching contemporary capabilities, but I have no doubt that it will be mainstream discussions in a decade. I mean, we'll look back at today and laugh at people going about 2 or 4 processors in the system and limited scalability when interesting new technologies appear. Certainly, cell matrix type logic sets the stage for all of that. But I'm going to back up time a little bit and pretty much talk about what is capable, what we can do today in self-configurable systems. And 2 aspects are agile hardware and embedded computing. This is a talk that I gave. First time I gave it was about sometime in January. This was a graduate seminar at BYU. And they have a fairly sizable configurable computing group out there. So agility with regards to computing pretty much attaches itself to software. We think of the agility of a platform is pretty much provided by software. The fact that software gives us the ability to change its functionality pretty quickly within a few clock cycles. In a few clock cycles, we can jump to a new subroutine, radically change the operation of the platform by having system interrupts, some kind of software exception, or so forth. And it does a pretty good job. And the embedded computing aspects, I want to set aside desktop computing, big iron computing, and focus on things that are untethered for the most part, or tethered weakly, wireless Wi-Fi or something like that. Or maybe just totally autonomous, flying out to Pluto. And we don't have too many agile hardware systems today. I'd like to explore. If we did, what could we do with those? What they look like. So many contemporary appliances have lots of embedded computing aspects of it. One in particular I'd like to just zoom in on a moment is the iPhone. Anyone here have an iPhone? I assert that this is probably the best example today of an agile platform. This is pretty much the most flexible device in the market. You can argue, well, the BlackBerry is more agile, but this particular class of device is extremely agile. At least it seems agile. And hardware-wise, we've got all sorts of features. But if we look under the hood, the agility does not come from hardware aspects. So I'm just digging out on the web. This is the guts of a first-generation iPhone. There's not that much in it. If you look at it, there's some cheap display, electronics, inexpensive antennas, logic board is just a minuscule device. It looks very nice, and the battery looks like the biggest component in the device. Looking at the computing platform a little more carefully, it's an ARM processor, maybe some proprietary chips, and some memory. So agility here, this is a moderately capable embedded processor. Agility is going to come in software. It's a pretty big device. Obviously, you can run operating systems on this and everything else. But it's not, the self-configurable aspects are not there. And in terms of agility, I'm going to assert that it's not as agile as it could be. And I'd like to look at one particular application in general. When I first saw this, it blew me away. I'm not sure if you're familiar with this. This is an application called Showtime. Ever hear of this? This is cool. This is you go shopping, go to Best Buy, see something you like. I'm sure whether that's a good deal or not. You pull up your iPhone, take a picture of it, and a few seconds later, it tells you where you can get better deals, price comparisons with looking at lists pretty quickly. Wow, this is just a commodity platform that can do a remarkable computation. Good morning. So let's dissect this a little bit. How does this application really work? Well, it's not. It's a pretty agile application. It's not dependent upon hardware agility on the platform itself. The way it works, it first starts out by taking a picture of a product, sends it wirelessly off to a server farm. The server farm does all the hard work, heavy lifting, feature extraction, rotation, light compensation, internal database search, and then external internet product search. And the last step is providing the results back to the user. All done with relatively low amount of time. Yes?
Does it send the entire image, or does it process it to reduce the size before it sends it
I have no idea. I'm guessing, based upon the simplicity of the ARM processor, it's not going to. Probably the only compression it does is a JPEG. I'm thinking, think of the designer, what the trade-offs that he has to make. The amount of CPU time and battery life he's going to expend doing feature extraction, data reduction, handheld versus longer transmission time, but very rapid extraction of the server. But I think that's exactly leading to where I'd like to go on this. So that particular application falls almost into the category of killer apps in terms of iPhone applications. You don't really need agility per se to improve upon that. They have a framework that works on that. But what if we had more agility in the platform? What if we folded it in self-configurability? What if we could do those computations in the platform instead of relying upon a third-party server to do that? For this particular application, look at all these computations that we have to do. We have to do image scaling, interpolation, rotate, compensate for slight skews, a lot of 2D window erosion, dilation operations. correlations, if you do feature reduction, doing correlations, database searches, nearest neighbor type of searches on that, following the actual lookup. It certainly would not pay for Apple to add in all these extra chips into the platform for this particular application. The added cost, size, weight of this would easily classify this as unworthy. But just think of it, if you could do these capabilities in the platform, do more responsive, maybe person identification, this name is over the phone. Maybe that could be helpful to show tell. We'd have to put our brains. I'm sure there's much more we could do if we would have more responsive platform to do these types of things. That's kind of uncertain. So, I'd like to propose that we could gain more hardware agility. Greater hardware agility would open new opportunities for FWG. So how does agility provide a gain? Well, in this case, we're talking about is our computation time, and that's just one dimension. There's other aspects of fault tolerance. So many of the aspects of what cell matrix provides, not all of them, of course, but in this particular example, by providing more efficient computation, higher response, it's likely that you could open the door for capabilities that were otherwise unintended. So, since we're just looking into the near future, not the far future, I'd like to look at mechanisms for achieving hardware agility. And we'll look beyond the obvious configurable computing aspects. Talk about FPGAs are probably the best thing that we have right now to achieve at least some degree of hardware agility. Some of the aspects of looking at these things a little differently. We've got hardware that's controlled by RAM cells. Each RAM cell is controlled by software. So essentially, we do have hardware that's under the influence of software. In theory, provides us the mechanism for self-configuration. But the use model today for FPGAs is pretty much rapid prototyping. I take my HDL code, crank it down, turn the crank, and it appears on the FPGA. Or ASIC replacements. If I don't have the time or the budget to form an ASIC, I'll use an FPGA instead. Where are you guys in the program? Have you all been exposed to FPGAs? So, FPGA building blocks, I'll dwell upon this. I've seen this before, but it's pretty simple lookup tables and flip-flops. Obviously, very similar, at least in theory, to the structure of cell matrix, but more of a loaded cell than compared to a cell matrix. But so, I think cell matrix is the right way to go when we look out into the future. But what we have today, we certainly do have something that can provide some of the functionality. Maybe one point in this, when we look at FPGAs, we're so logic-centric, where we have gates and slices and utilization of flip-flops and so forth. But an important perspective is that the logic aspects of an FPGA are so minuscule compared to routing. An FPGA is 80–90% routing, programmable routing resources, and logic's just kind of little stuff that's sprinkled out on one side. And in contrast with cell matrix, I think the cell matrix approach is pretty logical. Well, if you're spending so much in routing, is there stuff in the substrates that's really backing up the logic? Can we put transistors and essentially make our routing cells programmable cells like a cell matrix? This is not a physical die shot of the device. This is a logical FPGA editor shot. So we really don't know how. Well, physically, it does correspond. This is a small amount of the actual logic, but the actual substrate usage, I mean, here it kind of implies that there's nothing on the substrate other than maybe a few switches here, and all the wires are above the substrate. The utilization of the actual switching material of the FPGA is low. And it just gets worse. So a center tile, the building block within the FPGA, there's close to 800 wires. But as we get to larger devices, the number of wires quickly goes well above a million. These days, it's closer to 20 million programmable wires per device. And the actual logic cells themselves, actually that little yellow dot is 4 of them. I could draw a small drawings that represent. So these resources are pretty plentiful. See the timeline approaching to the right-hand side where these things are going to be very disposable and cheap. But getting back to the theme, here's probably why we don't see agility, self-configuration, and contemporary devices. The mindset on designs has been just rooted way back into VLSI, chip design, basic design. And the flow is, well, you sit at your terminal, you crank out HDL code, you simulate it, the system, and everything like that. Hit the button to implement. There's no reverse. Implement goes down into the platform, and the platform can do some more debugging and so forth. Not very good for self-configurable systems. You can't put the stuff on the left-hand side, or at least in the conventional flow, put the stuff on the left-hand side to the right-hand side. Once we get into the right-hand side, we're kind of stuck. So embedded agility is pretty low. And if you look at the design flow, if you've done FPGA designs before, maybe in class it's pretty simple. You just hit a few buttons and you get your design. If you're doing a complex design and you're pushing the limits of the device, there are lots of other steps that you need to go through. And it's a pretty complex process. And it might justify the fact that when you install the tools, you consume gigabytes of disk space. There's just so many tools and steps along the way. This is nice. It works, but is not a good model for self-configuration for agile hardware for making things work within that device itself. So the observation here, which I'd like to explore alternatives to, is that we're constrained to create FPGA designs using the conventional desktop VLSI flow, where none So the remedy is to completely rethink the way that, at least in the short term, if we want hardware agility, completely rethink the way designs are made. And we can do all the thinking we want if the FPGA vendor tools don't cooperate with this and allow us to do exploration. We're kind of stuck unless we do some weird things. And that's what I'd like to explore a little bit right now is a couple of weird things that we're doing up in the lab. I'd like to introduce a project called Wires on Demand, and in this case, applied to radios. And it's a different use model for FPGAs, not self-configurable, but kind of enabling the aspects of self-configurability. And the other project I'd like to dig into is autonomous hardware for FPGAs. And that is a little more self-configurability, but perhaps less responsive, less dynamic than one of the book. So let me start with the first one, Wires on Demand. Has anyone seen this in any of the other presentations? Has anyone discussed this at all? I don't think so. Focused on myself. So this is a project in which we'd like to have more hardware agility. We'd like to do, like to allow the platform to participate in its own design. And the approach here is that, at least the design model is that the designer still writes HDL code at his desktop. But instead of writing the whole application, all he writes is the building blocks. So like radios, you might do filters, modulators, mixers, signal synthesizers, and so on. Very much like in the software, drawing analogies to software. You do software developments, maybe you, in a large project, designers build up libraries, DLLs, dynamic think libraries that go into the target platform. One designer does not design everything. Designers build components, and at runtime, when components are needed, they are assembled, bound into the system. Connectivity, both connectivity and software, as through data transfers. But we'd like to use that same model in FPGA designs if possible. So the idea is that on our spacecraft going to Pluto, we've got our an engine running in the platform in software, or maybe in hardware that monitors it itself. Maybe when it encounters something new, it knows how to modify itself, bring in new functionality autonomously without external intervention. So in this case, building blocks are DSP components. They are assembled, placed, and routed as needed within the embedded system. And for radios, if we're modifying radio functionality, we can't take 5 minutes to do a modification. We can't take a minute. It would be very inconvenient even if we took a second of downtime on a radio to reconfigure it. So it's got to be really fast environment. We got to do all the desktop stuff in terms of place and routing. We got to do that very quickly within a second. Does that make sense? So here's a little cartoon sequence on how it works. Well, at least this is a web interface. This is a toy interface to the actual environment. This is a snapshot of what's in the FPGA. These dark green columns are memory blocks, block RAMs within the FPGA. This light green column is the DSPs. This is where the multipliers, the signal processing does, are within the FPGA, in this particular FPGA family. And so I want to build radios, and at least in this case, I'm going to hang out with these light green stuff because radios like to be multiplied accumulates, and I like to use DSPs to do that. So within the without external control, I can instance library components, and when the components are instanced, connectivity, routing between them is formed, and whole chains can be modified and resized as needed. So this is done within the device itself. All the processes that are needed is to go into libraries, pull out components, relocate them within the fabric, instance them. Once they're instanced, use the hardware, call a router to connect them up. And once they're connected up, bring the system online. For someone that has not done FPGA design, I guess their reaction is normally, well, yeah, isn't that how you're supposed to use FPGAs? They're dynamic logic, like, isn't that a standard use model? And unfortunately, it isn't. And there's a lot of awkwardness in doing this, but this is a pretty neat system. And the flow, there are two flows here. The desktop at design time and the run time. At the desktop, the way you do designs is pretty straightforward. It doesn't differ at all from normal design, except you're just doing library components. You write your stuff in your favorite HDL or package, whatever package you wish. And at the end, you get a bit file. In this case, though, it's not a full chip bit file, it's just a small little bit file fragment. And then there's just magic in the middle that constructs all this stuff. In addition to the output design, you get cataloging information so that runtime searches can find out properties of the device in terms of its size, where the pins are located, and how to be located within the resources in the chip. So that's pretty straightforward. The flow for doing self-configurability within the FPGA itself is a little more complicated. We start on the right-hand side, where we discovered that we need something. We make a request, and these things could be locally in the platform itself, within the FPGA, or it could be a network request. We make a request. There's a search to see if we can satisfy the request. The request is possible. Library components are pulled in. Properties of the new components are analyzed, and the existing design is analyzed. Where do we have room to place this new library component? So we go through a placement process, and then once we've decided on placements, we know where the pins are and how it has to connect with everything else. We invoke a router, and it will then create a new bit stream for the device. The bit stream then comes back and partially reconfigures the radio. In this case, it's already functioning. And it has, as I said, it has to be dynamic. We have to do all these steps in a second or less in order to be reasonably responsive. And so this is a pretty fast system in terms of performance. So this column right here, group of columns represents what the desktop tools provide, and here's the embedded system and its performance. The rows here represent simple cores, simple blocks, library elements that are built with both systems. And some of the properties of the design are shown here. Delays of after it's placed in route, how fast is the components. How much memory is used by the system in order to place in route to build it. The amount of time that it takes to execute. And average number of segments is the kind of a performance metric for the router. Here's my source and here's my destination. How many hops do I need to go from source to destination? And the larger this is, the less efficient, the less intelligent the router is. So if you compare these things, the delays are for the embedded router aren't as good, but not bad. 10-20% off. The amount of memory used when I fire up the Xilinx tools to place and run my design, it looks like that I need a quarter gig just to get things going. Here I'm 1,000 times less with a quarter meg of memory needed to get the job done. Execution time, about 20 seconds, 17 seconds, 20 seconds to get the job done, compared to 1 or 2 milliseconds with the embedded platform. The overall performance of the routed routes are quite comparable. So, in the platform, self-configurable system, external system, internal router looks pretty good. That's where most of the work is done. It's no free lunch. This is a little deceptive in the fact that this internal router is not as fully capable as the desktop router. It's not geared to do whole chip routes and a lot of aspects like that. But I don't need that capability. So if I flush all the extraneous desktop processing away, what I get is a lean and mean router that I can place with my device. So 10,000 times faster, 1,000 for the memory footprint. Memory, of course, is important in terms of its footprint, or in terms of if you're in an embedded system, you've got to be fairly efficient with it. The teams up in the lab have been using this. Well, they have a project called the Rapid Radio Project, in which they'd like to just take a snapshot of spectrum, radio spectrum, draw a box around a signal of total unknown properties, alien ETs phoning in. Draw a box around this, hit a button, and let the system design a full receiver for that. Do a lot of guessing of what type of modulation is going on, what's going on behind the scenes, and instantly build a receiver to pull that signal. The Rapid Radio Project has not gotten to the point of using the wires on demand yet, but we hope to get there. Another project, autonomous hardware for FPGAs. This is a project that one of your classmates, Ways, is digging into. So this is more pure in terms of what the theme of this course is in self-configurability. Autonomous computing systems. And I'm not sure, I'm looking through the videos, I'm not sure if Nick has really gone into this enough yet. Folks in the class has been on capabilities, low-level functionality. I'd like to mention, step up a little bit in what's it good for, what are properties of self-configurability for unknown applications. So autonomous computing, take something and fly it to Pluto, or something that doesn't have the privilege of being connected, at least in a strong sense, to a design. Autonomous computing systems function with a large degree of independence. Assumes a large amount of responsibility for itself and its operation. So we might give it guidance and rules on what to do, but its actual execution is determined by itself. And the third point is important. It absorbs much of its complexity into itself. So the external world of a view of an autonomous system is something that can function, can survive a failure, redesign over faults, or add new sensor capabilities without user intervention. Under the hood, though, that process might be much more complex. And autonomous system detects and responds to internal and external conditions. External conditions, I'm going to Pluto and I see some alien along the way, I'd like to talk to him to figure myself to do something, to establish a new sensor, bring a new sensor online. Internal conditions get smashed by radiation, and unfortunately my chip goes bad. How can I recover from that? Tag portions and stuff like that, and bring other functionality online. So in our case, I'd like to explore this with contemporary technology. In our case, we have to, in order to achieve autonomy, we have to be, to a certain degree, self-aware in the fact that we have to know, if I want to modify myself, I got to know what I am, what resources I'm using, and what resources are broken, and what resources are free. So an FPGA line, in the world of FPGAs, what slices are in use, what routing connectivity is in use, what are the bad sites, and so on. So autonomy, I want to be able to add new logic gates, make adjustments to existing logic gates, and obviously this looks a little different than the normal FPGA design flow. So a prototype system was built in our lab about a year ago, and pretty much just assumes two things: that you have an FPGA and that you have an external memory attached to it. Maybe a clock, maybe that's another thing. But that's it. That's it. And impose some kind of rule, some kind of mission into the device. And the system is capable of compiling new designs, finding places to place them within itself, connect them up to existing logic, and then to bring that new functionality online. So not only do we need these capabilities, we also need a place to build it. So there's a sandbox to respond to. So the system can respond to some kind of external stimuli, for example, a sensor, a new sensor needs to be adjusted. I could just convey logic to the device, high level netlist speed. In other words, my system can be complex, and if I want it, if someone else wants to bring functionality into the system, that person doesn't have to be aware of the complexity inside. Just provide a high-level abstraction of what functionality I need to bring online. I'll deal with that complexity. I'll compile it down and process it. Likewise, if a fault occurs, maybe I can respond to that and change functionality. more detailed at this, in this first generation, this was implemented on the Vertex 2 FPGA, Vertex 2 Pro FPGA, and that FPGA has lots of configurable logic and a small processor at the scale here. So we're going to put a lot of things, functionality into that processor that's within the chip. We're going to run Linux on it, and we're going to put Java. In this case, we'll do a lot of, at least in this implementation, we use Java as the engine for doing all this stuff. So Linux run Java, and under Java, all these other functions. This is necessary in external network connectivity, but within itself, it can. Edith is a language, netlist language that is standard among the EA community. We chose to use that as the means of the base description of everything. Connector, bringing circuitry online, placements, routing, implementer, compiling the design, and being able to talk to itself. This differs from the previous project in the fact that the previous project used large library cells and simple routers for connecting them together. This has a holistic view of itself to its the finest detail. We're not doing library assembly, we're doing full modification of anything within the device. And I'm going to quickly just, here's a cartoon of showing this thing in operation. It's running Linux, and there's a command line interface. There's a command line interface to the autonomous engine within the device. So this gives you a window of high-level functionality, and I think it also conveys the fact of how these functions can be scripted. So, for example, I want to build a counter. This says there are 3 commands here: parse an EDA file. Parse an EDA file, place it somewhere within the device. Is the second command. Route up the counter so it's placed it and it's routed up internally, and configure the counter. Actually deploy it into the system. And we want to make some blinky lights flash with this counter. So we do similar commands to configure I/O ports. Make it responsive to dip switches. We do another command to configure more I/O port functions. And then connectivity. Here shows the nature of connections within the system. In this case, I'm connecting up a clock, system clock goes into the counter, and broader connectivity is done. Connects, in this case, some buses, and I've got 3 sinks, or 1 source and 2 sinks on this particular network as specified on that command line. I can destroy routes. Disconnect is a script command, and more connect commands bring things together. So within the device, I think you can envision the fact that if I have these high-level functions provided internally, I can make higher-level decisions on what I need to do, what to do. Just a shell script within the device. Use models for this. If I see a portion of my circuit has failed, I can respond by disconnecting it from the system, building a new circuit somewhere else, and bringing that function online. Another use model is doing system discovery. If I have my system and I present an external sensor or a device to it. You can go through a discovery process and, in this case, discover that I just sensed a camera interface connected to my perimeter. I know what that is. I'll build the interface. I'll bring that interface online, perhaps other functionality online, and upgrade the system. So it's pretty powerful in that respect. And this is a working demo from the system. Performance is my last comment here. I want to compare the autonomous system with the conventional flow, in this case a quad-core desktop machine, and everything running on the embedded processor within the FPGA. I've got, I want to play with a bunch of EDIF files here, decoder, counter, a mouse, a PS2 mouse to core, a video core, and look at the complexity of the EDIF of these. And I'm going to just take these systems, apply them to the mainstream tools, apply them directly to the FPGA and look at the responses. Here's the adaptive system response. Here's the desktop system response. This is the speed of the resulting synthesis run here. So we count the decoder module, run up to a gigahertz according to that, and utilization, and the amount of time that it took to compile that design. Well, performance isn't all that, is 10 or 20% lower of the fully embedded system. Utilization is pretty close here's the desktop and the embedded system. The compilation time, how long it takes to actually understand, place, and route the design, is a bit slower. It's significantly slower. In this case, the worst case here is 14 times slower. But heck, I did this without a desktop machine, without gigabytes of memory, hard drive, space, network connectivity. If I'm on my way to Pluto, what else am I going to do? So it's pretty good in that. Last slides. This is a capability that has not really been explored yet in our world. I mean, we have the technology available to us, but I think it's been more of a tool issue in allowing us to explore that. So we need to break away from the ASIC replacement view, at least in our short-term timeline, and explore different use models for FPGAs. And really, last slide, too much hardware agility could be a bad thing. And I said, any questions? Well, I would help with sorry. All right. And I said, any questions?